Okay, next we are going to look for the properties of regions of convergence. Okay, the property of the regions of convergence. ROC of a signal does not contain any of its poles. Okay, so basically I already covered just now. Okay, inside a region you cannot have another poles. That is why if we have 3-4 poles, we are going to have several number of two-sided region. Okay, so the ROC of a signal is a circular ring in the complex sequence. Okay, it is shown through this one. Okay, here you can see that. Okay, it is circular ring. Okay, the poles is represented by a circular ring. Okay, next, a boundary of ROC is the circle modulus Z equal to modulus A, where A is a pole of XZ. Okay, meaning that, okay, just now I did mention that for the ROC, we just consider the positive side part. Okay, meaning that that is why we have modulus. Same goes to the poles value. We just consider at the positive side. That is why we have modulus at the poles value. This is only for ROC. ROC, we just take region at positive side. Why? Because of we need to have causal sequence. For Z transform, to avoid convergence condition, we need to have a sequence at the right side part only, at the positive part only. Okay, so next, the ROC of a finite duration and absolutely summable signal is the entire Z plane. Okay, so that one is very easy to understand, right? Okay, next we move. Okay, this is basically the definition of right-sided, two-sided, and left-sided. Okay, so for right-sided region, the ROC of right-sided signal Xn is the region out to the outside outermost pole. So right-sided, the region is outside outermost pole. Okay, for left-sided region, it is a region inside innermost pole. For two-sided region, it is the region in between two poles. Okay, so this is important part. You by hook, by crook, make sure try to remember this definition. Okay. Okay, next. Okay, similar to DTFT. Okay, we have the properties for the Z transform. Okay, so we have linearity, time shifting, scaling in Z domain, time reversal, time expansion, conjugation, convolution, differentiation in Z domain, and the initial value theorem. Okay, so basically linearity is actually the same. Okay, what you have to do is you just have to replace your n with Z. That's it. Okay, next. Okay, but for you to ensure it is linear, make sure it is the same constant. It use the same constant, and there is no time shifting. Okay, so it is linear. Okay, so next, okay, we have time shifting property. Okay, for time shifting, okay, for example, we have xn minus n naught. Okay, for example, we have xn minus 1. So Z transform of xn minus 1 is, okay, you have time delay, time shifting. So time shifting of minus 1 is Z minus 1. Okay, the Z transform of Xn is Xz. Okay, same goes to 3Xn plus 2. Okay, so 3 is a constant. Z transform of a constant is a constant. Okay, next you have time shifting plus 2. So you're gonna have Z to the power of 2. Next you have a function Xn. So you have Xz. Okay. Okay, maybe I give you one more example. We have Xn minus 2. Okay, so we're going to find the Z transform. So constant, constant. Okay, and then we have time shifting. We have Z minus 2. And then we have Sn function. So Z transform of Xn is Xz. Okay, and then we have time scaling. Okay, so for time scaling, it is actually frequency shifting. Okay, in time domain. So for the Z transform, you have like this one. Okay, for time reversal, okay, if you still remember in your DTFT, okay, okay, you have X minus n. So in DTFT, we're gonna have X exponent minus j omega, right? So for the function, okay, but for Z transform, instead of we put Z minus 1, we replace Z minus 1 with 1 over Z. Okay, time expansion, same thing. Okay, nothing different with DTFT, only the function. Okay, instead of we use exponent j omega, now we use Z. Okay, next, conjugation, same thing. We have conjugate in time domain. So basically in Z domain, you need to do conjugation for X and also for the Z. Okay, differentiation in Z domain, same thing. Okay, now this is important. Okay, analysis and characterization of LTI system using the Z transform. Okay, so basically, okay, for example, this is your Xn. Okay, and how to get your Yn? It is Hz multiply with Xz. Okay, why we have conjugate? Because of your Sn is in time domain. Okay, so basically, how to know how to get your Xz? So from Xn, you have to use Z transform. Refer to your property table. And here for LTI, for linear time invariant system, your Xn is the eigenfunction of LTI system, and your Hz is the eigenvalue of LTI system. Hz is known as a system function or transfer function. So how to get Hz? Hz is equal to y over x. Frequency response, Hz with z equal to exponent j omega. So basically, it is also known as frequency response if yours because now in the definition we replace our exponent j omega with z. Okay, this is another important thing in chapter 6. Okay, for each ROC, you need to determine the causality and the stability of the system. Bukan you need, you you can determine the causality and stability of the system. So basically, based on the given determined ROC, from the determined ROC, you can determine causality and stability. Okay, so if you read through here, okay, LTI system is causal if your Hn, your impulse response Hn equal to 0 for n less than 0, which is right-sided signal, or in other words, ROC of its system function Hz is the exterior of the circle including infinity. Discrete time linear time invariant system with rational system function Hz is causal if and only if the ROC is exterior of a circle outside the outermost pole, and with Hz expressed as ratio polynomials in Z, the order of numerator cannot be greater than the order of the denominator. So basically, the ROC, the region is causal if the region is right-sided region. Okay, I repeat. The region is causal. Region is causal if the region is right-sided region. So basically, for ROC, the region is causal if the region is right-sided region. What happened to left-sided? What happened to left-sided, two-sided signal? Two-sided region? It is actually not causal. Why? Because based on the definition, ROC is causal if the region is exterior of a circle, or in other words, it is the region is outside outermost pole, which is referring to right-sided region. Okay, for this part, Hz is expressed as ratio in Z in order that numerator cannot be greater than denominator. Means your Hz, the polynomial, the function for Hz must be, for numerator part, must be less than denominator. For example, your Hz for numerator part, the highest order is -2. For denominator part, the highest order is -3. So what happens if your numerator part is Z -3, but for your denominator part is Z -2? So what you have to do is you need to do long division. Okay, next, ROC condition, stability. Okay, LTI system is stable if and only if its impulse response Hn is absolutely summable, or Fourier transform of Hn is converged, or the ROC of the system function includes the unit circle. For causal LTI system, all poles Hz must be in the unit circle. Means the region is stable if the region includes unit circle, which is modulus Z equal to 1. Okay, meaning that, for example, let's say if you have ROC for right-sided Z greater than 2, and then you have left-sided Z less than 0.1, and then you have two-sided, your modulus Z is in between 0.1 and 2. So you need to determine causality and stability for each region. So basically, for right-sided, okay, it is causal. Why causal? Because it is right-sided region. Okay, is it stable? Not stable. Why? Because the region is greater than 2, so it is not include unit circle. Okay, so next, for two-sided, it is not causal. Why not causal? Because it is left-sided region. For left-sided, is it stable? It is not stable. Why not stable? Because it does not include unit circle. For two-sided region, okay, so two-sided region, is it causal? Not causal. Why? Because of it is left-sided region. Two-sided region. Is it stable? Yes, it is stable region because the region includes unit circle. Done. So that's all for chapter 6. Okay, so stay tuned for examples, more examples.